Welcome back. In this lecture, we're going to start discussing the microscopic theory of bosons, writing down Hamiltonians and actually trying to solve them. To do this, we're going to need the technique of second quantization, and for that reason, we're going to need mathematical preliminaries introducing the technique of second quantization. Now, I know a lot of people who might be watching these videos are familiar with second quantization and have used it previously and probably don't need so much a review, but I find myself that I often need a review because some of the fine details, particularly where you put the complex conjugations, that I always get it wrong unless I go back to the beginning and start over and refresh everything in my memory. So this is going to be really, for most people, probably refreshing your memory. If you've never seen this before, this will give you an idea of what we're doing, although I can also recommend some places to get more practice with second quantization as well. So email me if you need those references. So let me start by quoting the great Sidney Coleman, great teacher, my field theory teacher, among a whole generation of scientists. He taught field theory, and he was well known for saying that a student's experience in physics is that of solving the harmonic oscillator each year at increasing levels of abstraction. So this year we're going to solve the harmonic oscillator using ladder operators, and that is how you start introducing second quantization. You start with ladder operators for a single harmonic oscillator, for a simple harmonic oscillator, SHO, and the ladder operators, you know them well. We call them A and A dagger. Usually, they have commutations of one canonical commutations. We can write down states n, which are defined as the nth excitation of harmonic oscillator, 0 being the ground state. Probably spelled oscillator wrong there. And the magic of second quantization is that the nth excitation of a harmonic oscillator is exactly equivalent to saying there are n bosons in this orbital. So the connection between bosons and excitations of a harmonic oscillator, if you've never seen it before, is an extremely deep statement. I think it's most transparent in the context of phonons, where phonons really are made up of harmonic oscillators, and then you realize when you quantize it, everything looks like particles, which are bosons. But the connection between excitations of the harmonic oscillator and bosons is both mathematical and physical. At any rate, the nth excitation state, the ket n, we can write in terms of the ladder operators as a dagger to the n over the square root of n factorial on 0. The square root of n factorial so it comes out normalized, and this makes an orthonormal set of excitations of the harmonic oscillator. It actually makes an orthonormal set spanning the whole Hilbert space of the single harmonic oscillator. And we can write a number operator which measures the number of bosons in a state, or the excitation level of the harmonic oscillator, as a dagger A, which is the number operator. Okay, probably everyone knows this if you've studied quantum mechanics in a good course. The second step we would like to introduce here is the idea of a coherent state, which is useful for many things. A set of states for describing your Hilbert space of a simple harmonic oscillator, and we'll call it alpha, and I'll put the subscript C here for coherent, although I may end up dropping the subscript C later if it doesn't cause confusion to do so. So the state alpha subscript coherent is e to the alpha a dagger on 0. So alpha is some complex number. You can define it for any complex number. And the way we define this exponential of an operator is by expanding the Taylor series. So this is 1 plus alpha a dagger plus alpha squared a dagger squared over 2 factorial plus alpha cubed a dagger cubed over 3 factorial dot dot dot, all applied to the vacuum, the zero state. Now we can let these terms act on the vacuum, and then rewrite the result that we get out in terms of the kets n, these kets n up here, these guys, write it in terms of these guys, and we'll get, well, okay, the first term 1 gives us just 0. The second term, alpha a dagger 0, gives us, well, the a dagger on 0 gives me the 1 ket, and the alpha is out front. And then we'll have an alpha squared. There's a square root of 2 in the definition of the 2 ket up here. So that will leave me with alpha squared over square root of 2 factorial times the 2 ket here. Is that clear? Okay. Plus dot dot dot. Okay. Now, a couple things to notice about this series. It's a superposition of different number of bosons in the state, or a superposition of different excitation levels of the harmonic oscillator. And the prefactors here, these prefactors, which are generally alpha, call it alpha to the m over square root of m factorial, depending on the value of the coefficient alpha, these will be of different size, but you can show that the prefactor peaks is max at approximately alpha equals square root of m. Okay, so when you get to the mth term, or m equals alpha squared, when you get to the for a given alpha, you go out to the mth term, which is roughly magnitude of alpha squared, and that is the largest prefactor. So that's the, among this superposition of many number states, that's the largest contribution, and others are smaller. Okay, now a couple other things to notice about this, this coherent state. The coherent states are not normalized in the usual way. So alpha coherent is not 1. In fact, it's easy to check. This is a nice exercise to try if you haven't done it. It's either the absolute alpha squared, which generally is not equal to 1. Matter of fact, it's not equal to 1 except for in the case of alpha equals 0. And furthermore, we have the fact that alpha prime coherent states are generally not 0. Different coherent states are generally not orthogonal to each other. So it's an inconvenient basis for certain calculations because it's neither normalized nor is it an orthogonal set. Nonetheless, it's convenient for some other reasons. So let's try to find out why the coherent states are useful. So let's take this expression here and copy it downstairs. So I apologize for doing this. So I realize that when I scroll things up and down, it's inconvenient, but let's rewrite alpha coherent. Looks like this. The point of a coherent state is that if you apply a lowering operator, alpha, we usually put the C outside, sub C like this. Did I mess that up here? No, I got it right there. Okay, sorry for the scrolling up and down. If I apply A to the coherent state, well, okay, what happens? The zero state gets killed, so this thing goes to nothing. The one state gets turned into a zero state by the lowering operator. The two state gets turned into a one state with a factor of square root of 2. Recall that A on, oops, let me move myself out of the way here. Recall that A on a state n is the square root of n times the n minus 1 ket. So if I apply it to the 2, I get square root of 2 times times the 1 ket. So then I get alpha squared times the 1 ket. And then if I keep going, the next term would be alpha squared over square root of 2 factorial times the 2 ket, and so forth. And I can regroup this to get to be alpha times that whole thing here is just the coherent state alpha. Let's get rid of the brackets. So the point is that alpha c is an eigenstate of the lowering operator with eigenvalue alpha. Coherent in that the c goes outside, like that. Okay, so that's the point of this of using coherent states. Okay, now why is that nice? The reason that's nice is because effectively, for many calculations, this allows you to turn operators A into numbers alpha. Okay, so let's see how this works. And conversely, A dagger will be turned into the alpha star. Let's see how that works. So the way that works is that A dagger on alpha will be alpha on alpha, and if I have an alpha bra over here with an A dagger on its right, that will get turned into alpha bra times alpha star. Okay, so let's see why this is convenient. Let's try to do a calculation. Let's do a calculation of the expectation value of the number operator, in the coherent state alpha. Okay, the coherent state alpha. So what's that? Well, it would be alpha A dagger A. That's the number operator alpha coherent state. And remember that the coherent states aren't normalized, so we have to normalize it properly. Coherent states like this. So let's think about what we get here. Well, here the A applied to alpha turns that A into a factor of alpha, and the A dagger applied to the alpha bra turns into an alpha star. So I end up getting alpha squared out front times alpha coherent over alpha coherent, which is just alpha squared. Okay. Do another exercise doing the same thing. Let's look at the operator n hat squared, the square of the and incidentally, this statement here that we just calculated was that the expectation of n is equal to alpha squared was agrees with the statement I made a little bit earlier, scrolling back up, that the prefactor peaks at alpha squared is the mth term. So it's not only that it's the most highly represented ket, not only is n the highly most represented ket when n equals alpha squared, but the expectation of n is also alpha squared. So let's now try to calculate n squared as an operator in the coherent state alpha. So we have alpha A dagger A squared alpha. Let me actually write it as A dagger A alpha divided by alpha. Now here I need to commute the A daggers to the left and the A's to the right. So this will then be alpha, and then we have A dagger A dagger AA plus A dagger A, just using commutation relations of the raising operators, alpha, alpha. And let's up smaller again. So once I'm here, I can take the two A daggers, apply them to the left on the alpha, get alpha stars. The A's on the right get alphas, and end up with alpha to the fourth, absolute value alpha to the fourth, absolute value alpha to the fourth, plus absolute value alpha squared. Okay, so the variance of the number in a coherent state is square root of sigma n squared is then the square root of expectation of n hat squared minus expectation of n hat squared, which is then just the difference between alpha to the 4 squared plus alpha squared minus this alpha squared, and that gives me the alpha squared cancels the alpha to the fourth, and I'm left with just alpha squared, square root. Okay. Equals. Did I do that right? I think I did that right. Yeah. Okay. So this is actually quite important that for large n hat, the fluctuations are much smaller than the average, than mean. That the mean goes as alpha squared, and the fluctuation goes only as alpha. And the reason this is important because it tells us that this often occurs in thermodynamics or statistical mechanics, that it's not going to matter if we fix the total number of particles in the system or not, because the fluctuation in the number of particles is much smaller than the mean number of particles in the system. Okay, so one thing, if you've never seen coherent states before, it's useful to know that laser light in an optical cavity is actually exactly a coherent state. One more thing that's really useful to know about coherent states is the idea that they have a number phase relation. It's useful for laser light, for superfluids, superconductors, number phase relation. And let's see how this works. Let's set the parameter alpha to be magnitude of alpha e to the I phi. Draw that phi better. Oops, e to the I phi. And then let's write out the coherent state associated with this alpha, exactly as we did before. Alpha coherent is e to the absolute alpha e to the I phi. Draw that phi better. There. A dagger on 0 on the vacuum, and let's write out this series. So this is 0 plus absolute alpha e to the I phi on the 1 state plus alpha squared e to the 2 I phi over the square root of 2 factorial on the 2 state plus ... And then if we take minus I d by d phase, d by d phi on the alpha state, on the coherent alpha state, well, what happens? Well, when you differentiate the 0 state, and this is not dependent on phi at all, so you get 0, so you get 0 times the 0 state. But when you differentiate this thing and multiply by the minus I here, this one brings down I, multiply by minus I, that gives you exactly 1. So we get plus 1 times alpha e to the I phi 1. And when we do the same thing here, this will now bring down a 2. So we get 2 times alpha squared e to the 2 I phi over square root of 2 factorial on the 2 state plus ... And you'll notice that this is exactly equivalent to the n hat operator acting on the n hat operator acting on the series, that the first term gets multiplied by 0, the second term gets multiplied by 1, but the next term gets multiplied by 2, and so forth. So this is exactly the same as the n hat operator on alpha coherence. So we can conclude that minus I d by d phi is actually equal to the n hat operator, meaning that these two are conjugate pairs. These are canonically conjugate. Canonical conjugate. Conjugate pairs, just like P and X. Remember that P is minus I d by dx. The same way here, N is minus I d by d phi. Okay, so that's a useful piece of information to keep in mind. Okay, so so far we've just had a single orbital or a single harmonic oscillator, and we've derived all of this material so far. Now, what we're actually interested in is a situation where we have many different boson orbitals. Suppose they're orthonormal boson orbitals. So we have many orbitals for bosons. As if you're a solid-state person, you might think about these as different sites on a lattice or something, where you can put a boson here, you can put it there, you can put it in another place. Call these positions I, J, and K. We can make bosons on any one we want, and we can have correspondingly raising and lowering operators, creation and annihilation operators for each site. So the commutation relations will be AI AJ dagger equals delta IJ, and also all the creations commute with each other, and all the annihilations commute with each other, equals 0. Okay, so this allows us to describe states with multiple bosons in them, and multiple bosons at multiple sites. So 0 is the vacuum, so this is no bosons at all. And we can have a dagger on site 1. So this is one boson at site 1. This is the site index down here. It tells you where the creation operator is acting. We could do a dagger 2, a dagger 1 squared on 0. This is one boson at site 2, 2 bosons at site 1. I guess if I was careful, I would put divided by square root of 2 factorial downstairs here to make it normalized. Okay. So seems like a simple generalization. Now we can start thinking about what happens if I choose a different basis of orbitals. So here I've chosen the I, J, K set of operators here. Index my operators with I and J. Maybe those are sites or something like that. But I can choose any wave functions I like, any orthonormal set of orbitals. So maybe I should have written this over here. So I is a set many orbitals orthonormal. I want to always work with an orthonormal set of orbitals. Write that down up there. But I can certainly have more than one different orthonormal set. I mean, some sets that are common to work with are plane wave sets. That's a nice orthonormal set. Or individual sites where you have your orbitals are localized at a single site. Those are known as tight binding orbitals. But there's many other types of orthonormal sets that I could use depending on what's convenient for my problem. Let's suppose I have 2 orthonormal sets. Normal sets. Sets of orbitals. Maybe let's write them as, I don't know, phi n and psi m. And these are 2 different orthonormal sets I want to work with. And I want to translate between them? Well, I can write the creation operator, or the raising operator, in the phi set, phi n, as a sum over the m states of the inner product A dagger psi m. And this is the formula that always gives me trouble. I always get confused as to if it's this matrix element or if it's the complex conjugation. This is the correct way to see it. We can basically, you're creating a phi orbital at the end of the day, not a psi orbital. Okay, let's do an example of this. For example, the most common example to worry about is the case where psi m is the tight binding orbitals. Tight binding orbitals. So these are a dagger at site R. So there's some lattice of sites R from a discrete set of R. Discrete sets R sitting on a lattice. And then the other nice set of orbitals that I want, psi n, is plane waves. I guess these can be e to the I k dot r, I guess, divided by the square root of the number of sites in the system. And this is created by a dagger k. And we can relate those two together to each other. A dagger k is 1 over square root of n, sum over sites r in the lattice, e to the I k dot r, a dagger r. Okay? K can be a vector, r can be a vector. It's always useful to remember that you can write any operators can be written in second quantization, can be written in second quantization. So for example, a one-body operator can be one-body operator. O hat can always be written in the form sum over n and m of the matrix element of O hat between orbitals n and m, create m, annihilate m, like this. And then similarly, two-body operators can be written in some form. O hat is going to be some set of matrix elements, a dagger n, a dagger m, AP, AQ, and so forth. Okay. All right. So it's very convenient to go one step further. We often, we start by thinking in the tight binding language. These tight binding orbitals we have. Imagine them on a lattice, and we then imagine going from the lattice to a continuum. This is something we very, very frequently do in condensed matter. You start by thinking about things on a lattice because it's easier, but then at the end of the day, you want it to be on a continuum. So you take a limit where the lattice becomes no longer discrete, where the lattice points get very, very close together with each other. So we can go from discrete to continuum, discrete to continuum. So our AR variable becomes, our AR operator, destruction operator, at position R, gets turned into, we usually change the notation. We make it psi hat at position R, but now R can live anywhere in the continuum. We also change the normalization a little bit. We take psi hat of R, psi dagger of R prime, and instead of this being Kronecker delta between R and R prime, we take this to be a Dirac delta function, R prime. It's convenient to do once we take the continuum limit. Okay, we can still write an expression for the plane wave operators, this is now going to be 1 over the square root of the volume of the system integral over all space, e to the I k dot r, and then psi dagger of r. This. Or in fact, we can convert any, and we didn't, I mean, here I converted from the second quantized continuum operators here, right, that are from the second quantized continuum operators to the plane wave orbitals, but I could just as well make a second quantized operator that creates in any orbital phi n as integral dr of phi n of r psi dagger hat of r. Okay, notice that the 1 over square root of v is part of this term here. It's if I want the orbital to be normalized, it comes with a 1 over square root of v. Okay. Good. In reverse, I can also write my continuum operators in terms of my complete orthonormal set. I can write, for example, psi dagger of r equals sum over n, any as long as it's a complete set. I can always do this. A dagger phi of n. I don't care what the complete set is, and this is sum over n phi star n of r a dagger phi n. And again, this is a case where I always get confused whether there's a star in this expression or not, but this is done correctly. Okay, so why have I gone through so much effort to introduce coherent states here? Well, it turns out it's extremely convenient to describe a Bose-Einstein condensate as a coherent state. Recall in a Bose-Einstein condensate, you're multiply occupying a single lowest energy orbital. So let's call that orbital phi naught equal lowest energy orbital. And I'm going to just change my notation very slightly. I'm going to write alpha phi naught to indicate that I'm filling orbital phi naught, and I'm filling it with a coherent state, the amplitude alpha, and this is going to mean e to the alpha a dagger phi naught, creating the a dagger phi naught creates a boson in the orbital phi naught, and this will act on the vacuum. Now we can, just basically repeating the calculation we did before, we can calculate the number of particles in that lowest orbital, and that will be, I guess, alpha phi naught, a dagger phi naught, a phi naught, alpha phi naught, divided by the normalization, alpha phi naught, alpha phi naught, and exactly the same calculation we did before, that the annihilation operator acts to the right, turns that into an alpha. The creation operator acts to the left, turns that into an alpha star, and this gives me alpha squared. So the coherent state puts a magnitude of alpha squared, number of bosons, in the eigenstate phi naught, and the fluctuation in the number of bosons is small compared to n naught, if n naught is large. Now we can calculate what the destruction operator at a point r does to this state phi naught by using our basis transformation. Let's just rewrite this destruction operator at a given point, and in terms of our basis of orbitals phi n of r, a phi n on alpha phi 0. The only orbital that is filled is the 0th orbital, at least in this wave function, this coherent state wave function I've written down. So I only have to consider the n equals 0 term in this sum. It brings out an alpha phi naught of r on alpha phi naught, and this tells me that the destruction operator r R is now turned into a number, gets turned into a number when it's applied to the coherent state, and the number it gets turned into, phi hat of R, gets turned into, I guess, the square root of n naught times phi naught of R, because alpha up here we decided is the square root of n naught, assuming alpha here is taken to be real. Okay, so this is nice. It allows us to turn these annihilation operators or creation operators into numbers, and that's why we want to work with the second quantized notation. So now, finally, after all of this, let us write down a Hamiltonian. Consider a Hamiltonian for many interacting bosons. For many bosons, H equals, well, we'll write down the single particle term, sum over particles I, pi squared over 2m, the usual kinetic energy, write that a little nicer, m, plus v of Ri. So there can be some potential as a function of position. Maybe in the cold atom world, we like to put the particles in a trap or something like that, and this v might also include a chemical potential that just raises or lowers the energy of all the particles if we want. And then the interesting part is the we'll write this way, factor of 1/2, sum over all particles ij. The interesting part is the interaction between particles I and j. So this is going to be, we're going to use this Hamiltonian many times. It's a generic Hamiltonian for particles with the kinetic energy in some background potential interacting with each other. The factor of 1/2 is so that we don't overcount particle I interacting with j and then j interacting with I. Okay, now this generic Hamiltonian, we want to write it in second quantized form, because that's going to allow us to use our machinery form, and we rewrite the Hamiltonian. This is sort of an exercise in, so to derive this it's a nice exercise in second quantization, but to give you a hint of how it's done, you transform into a convenient basis, and then once you're in a convenient basis, maybe even an eigenbasis of each operator, then you can, once you're an eigenbasis of each operator, then it's really easy to write down the second quantized version of operators. So for example, this single particle operator here can be written as psi dagger hat, the creation operator at position R, and there's minus h bar squared del squared over 2m. That's the kinetic energy term, plus v of R, psi hat of R. And then okay, so this is exactly the same, the single particle Hamiltonian in between psi dagger and psi. And the interaction term is integral dr prime, psi dagger hat of R, psi hat of R, u of R minus R prime, psi dagger hat of R prime, psi dagger of R prime. Okay, let me make a couple comments about this Hamiltonian. It's not quite right yet. It's almost right. So this term here is just the particle density at position R. So this thing here is the density at position R, and this is the density at position R prime. So this interaction term looks fairly natural. It's integrating over the boson density at R prime, U interaction between R and R prime, boson density at position R, and then there's a factor of 1/2 out front, because you don't want to, you don't want to overcount position R, interaction between R and R prime, and then R prime and R. That would be double counting. Now, this Hamiltonian, the way it's written, is not quite right. To make it right, we have to put colons around everything, and the colons are normal ordering operators. Normal order operators. And normal order operators means that you should shift all of the psi daggers all the way to the left and the psi's all the way to the right. Now, why is it we need that? It's actually easy to convince yourself that normal ordering has to be there. Why? Well, let's imagine that you have a system which has only a single boson in it, just one boson in the entire system. Well, without the normal ordering operators, you would measure a density at position r prime, and you would measure a density at position r, and you would allow the particle to interact with itself. It has a wave function that may be spread out between r and r prime, but you shouldn't allow that one particle to interact with itself. You should only interact with other particles. Now, if you normal order, instead, reorder in the opposite direction, so that if we wrote psi dagger hat r, psi dagger hat r prime, psi of r prime with hats, instead, this is how it ends up when you normal order it. Then this operator, in order to get something non-zero, you have to destroy one particle, destroy two particles, and then you put them back. So unless you have two particles in the system, you don't get any non-zero result, and that's actually what you want to have happen. Okay. Now, before going further, we have to actually choose what interaction are we going to use. And we're free to actually choose any interaction we want, but for many Bose-Einstein condensates, it's acceptable to choose a very short-range interaction. So we're going to choose u of r minus r prime is going to be some constant u times a delta function of r minus r prime. Now, for cold atoms, this is a very, very good approximation, that the cold atoms don't interact with each other unless they're really very, very close. And also for helium, helium-4, this is actually a pretty good approximation. As I mentioned before, helium at long distances from each other, two helium atoms, they interact extremely weakly just by van der Waals forces, and they only interact very strongly if they sit right on top of each other. So it's a pretty good approximation to consider it to be a delta function interaction. So that's going to collapse this term, these two integrals, to a single integral by making this u of r a delta function. So let me just rewrite this Hamiltonian, having made that change. So rewriting that Hamiltonian, we have again the single particle terms, psi dagger of r, then the minus h bar squared del squared over 2m plus v of r, and then psi hat of r, the single particle part, and then there will be u over 2, the delta function collapses one of the integrals, and I get psi dagger of r, psi dagger of r, psi of r, psi of r. So I've also implemented, here you can just make it a little smaller so you can see them both at the same time. Yeah, there we go. So I've also implemented the normal ordering by moving the psi daggers to the left and the psi's to the right, and then I've put the r and r prime at the same point because of the delta function. It collapses one of the integrals. Okay, good. Okay, so now let's take this Hamiltonian and apply it to a coherent state, in particular a coherent state representing a BEC. So we can write out the coherent state we're interested in, alpha phi, that's e to the alpha a dagger in the phi state on the vacuum. And so this is something that creates multiple bosons in the orbital phi. And the reason we wanted to write things in terms of coherent states is because when we work with coherent states, operators get turned into numbers. And in particular, the psi hat operator at position r got turned into, well, it was alpha phi naught of r. And we can say alpha is really just the square root of the number of particles in the state, square root of number of particles that we put in the orbital, expectation of the number of particles in the coherent state. And let's just define alpha phi naught of r, or maybe the square root. Let's assume the phase of alpha is real, so we can write square root of n naught phi naught of r. We'll call this phi of r, not to be confused with phi hat of r. Phi hat of r is an operator, and phi hat of r and phi of r is a scalar. But when we operate psi hat of r is an operator, and psi of r over here is a scalar. But when we operate psi hat of r on a coherent state, it gives us back psi of r, the scalar, as an output. So as a result, when we apply to this, when we take the expectation value of this Hamiltonian in the coherent state BEC, in this state here, it's just going to turn these psi operators into psi scalars. So let's actually do that. We have the expectation of the energy, by which we mean alpha phi Hamiltonian alpha phi over alpha phi is this is going to be exactly the same expression we had before, the single particle part, which is going to be minus h bar squared del squared over 2m plus v of r times psi of r, and then the interaction part u over 2 psi of r to the fourth. And the only thing that's different about this expression for the expectation value of the energy and this expression back here for the Hamiltonian is that here these are supposed to be operators too. These psi's are all operators, and here these psi's are now scalars. Okay. Now this is still slightly inconvenient to have a del squared sitting here, so let's integrate it by parts and rewrite it as in the following form. So this is h bar squared over 2m del psi squared plus v of r psi squared plus u over 2 psi to the fourth. And this is known as the Ginzburg-Landau or Gross-Pitaevskii form. This was constructed by Valery Ginzburg and Lev Landau in the context of superconductivity. Actually, somewhat early on, Valery Ginzburg won his Nobel Prize, I think in 2003 also, with Abrikosov, I think. Ginzburg's life is absolutely crazy. He barely survived his life in Stalinist Russia, being very close to executed several times, all sorts of crazy stuff. But he survived all of it and became a great physicist. Gross and Pitaevskii were working, Gross in the West and Pitaevskii in the Landau school, somewhat later on superfluid helium. They reconstructed this in a somewhat more formal sense using a second quantized technique, so it's named after all of them. What we do with this form is we minimize the energy. So we minimize or extremize the energy by taking dE d psi star of r equals 0, a functional differentiation. I guess that's the expectation of E up there. And that will give us, just taking the functional derivative of this equation, expectation of E here, the functional derivative of this equation gives us the following result, minus h bar squared over 2m del squared plus v of r plus u times psi squared, all applied to psi of r. Maybe I'll write this psi of r squared, all applied to psi of r equals 0. And this is sometimes known as the Gross-Pitaevskii equation. Or just a nonlinear Schrodinger equation. And see if we can understand what it is. Well, first of all, it looks like the Schrodinger equation. Let's get rid of this term for a second. Just drop it. Turn off the interactions. And then it looks like the Schrodinger equation, but there's no eigenvalue there. The eigenvalue is hidden in V, because remember, we can put a constant chemical potential inside V, so the energy or the energy eigenvalue is hidden inside V of R here. And the chemical potential floats up and down until there's a solution. Okay, this additional term here, this nonlinear term, which makes it the nonlinear Schrödinger equation, is the effect of the interaction. It tells you that the potential is higher in regions where there are already other bosons. So if there are bosons in some region, that means the wave function is large in that region, and the interaction of the one boson with the many other bosons that are already sitting there gives you this additional term, U times basically the density of bosons that are already sitting there, and it raises the potential in that particular region. Okay, one way of interpreting this Gross-Pitaevskii equation is that assuming we have a coherent state, a coherent state BEC, what it finds, the Gross-Pitaevskii equation, it finds the best value of psi equals alpha phi naught, the best orbital to put the bosons in. So you can imagine lots of different wave functions you could put all the bosons in. You can choose one of them that has the lowest possible energy, and the solution of the Gross-Pitaevskii equation is finding that lowest possible energy. Now, we went through a lot of pain to derive this. We had to go to second quantized notation, and we might ask, did we have to use second quantized notation to do this? Did we have to use a coherent state with an indefinite number of particles? It's like, did we have to use the grand canonical ensemble, which has an indefinite number of particles, instead of the canonical ensemble that has a fixed number of particles? The answer is that actually we could have used something with a definite number of particles, and we could have done things in first quantization to get exactly the same result. So let's write a trial wave function for a fixed number of particles, and we'll write it this way. Psi, this is a many-body wave function, is the product over I equals 1 to n, all n particles, of phi of Ri. Okay, so for some particular orbital phi, we're going to multiply the product of phi for all coordinates Ri. So we're making a symmetric wave function. It has to be symmetric because we're considering boson. And the symmetric wave function is basically putting all of the bosons in exactly the same wave function. All the coordinates are in exactly the same wave function phi. Okay. Now, using the first quantized Hamiltonian, I'll write it here again, pi squared over 2m plus v of Ri plus, I guess, 1/2 sum over ij u of Ri minus Rj. Wrote that before. Then let's just take this trial wave function here and find the expectation of the Hamiltonian. So many-body wave function, Hamiltonian, many-body wave function. And it's not too hard an exercise to convince yourself that, we have n bosons all in the same orbital. So the single particle piece is just n times integral dr of phi star of r, then minus h bar squared del squared over 2m plus v of r times phi of r. So n particles all with the same single particle kinetic energy, and then the interaction term. What is the interaction term going to look like? It will be plus n times n minus 1 over 2. That's the number of interactions. Each particle interacts with every other one. Integral dr prime. It'll be phi of r squared u of r minus r prime times phi of r prime squared. And these are all vectors, I guess, like that. Okay, very natural result here that we have n times the single particle energy, and then we have the interaction between the density at position r and the density at position r prime. So this, except for with the exception of the fact, what we did before was we took n, square root of n phi, and we called it psi of r, and except for this minus 1 here, this is exactly the same expression as we had back here. Exactly the same expression as we would have had here. Okay, except for the minus 1. And since we're considering n being large, we can usually throw away minus 1s. So either approach will give you the same energy, and if we functionally differentiate this expression with respect to the wave function phi, we'll get the same Ginzburg-Landau form that we had before. So we didn't actually need to use second quantized notation. And either way, we would find a way to optimize over the best single orbital phi that we could have possibly used when we write down a Bose-Einstein condensate when many, many particles are condensed into the same wave function phi. So why did we then go through all of the work to do everything in second quantized notation? Well, the reason is because the superfluids and Bose-Einstein condensations we're interested in are usually not non-interacting. We wrote down a wave function, we wrote down a coherent state, which is accurate for a non-interacting Bose system, but we have interactions in our system. Now, when we have interactions, it is we won't be able to put all of the particles in the same orbital. Why? Because if we try putting all the particles into the same orbital, some of them will be kicked out of that orbital due to the interactions. Okay, so it's not correct to write down a wave function where all of the bosons are in exactly the same orbital, because some of them are going to be kicked out due to the interactions. Nonetheless, it is still the case that the expectation of the annihilation operator will still be a good order parameter. This will still represent the effective wave function of the superfluid, or order parameter. And the Ginzburg-Landau equation will still be appropriate, at least as an approximation to the physics of this, or the Ginzburg-Landau or Gross-Pitaevskii equation will still be appropriate for determining the physics of this order parameter. So the point here is that by working in second quantized notation, we can still write down an order parameter or a wave function of the condensate without insisting that all of the particles are in exactly the same orbital, because we know some of them are going to be kicked out into other orbitals due to the interaction. So we'll pick up next time with some of that idea and try to describe this wave function of the superfluid, or wave function of the condensate, or this order parameter in a different language. Okay, I'll see you next time.